Hi, physics. Mr. Janowski here. This is homework 5, problem 5. So what's going on here? What is the initial velocity of a projectile launched vertically from the surface of the Earth that reaches an altitude equal to 2.00 Earth radii above the surface? So this thing is going up pretty fast, but it doesn't actually have escape velocity. So let's start with step What are we looking for here? So what is the initial velocity? So v initial equals question mark. And what units will velocity have? Meters per second. All right, so for this one, let's do step 1. We're going to make an initial and a final sketch. So our initial sketch. Bloop. Sorry, it's hard to write. So here's the Earth. We have some projectile, so let's make it look like a rocket. Boop. All right, hopefully that looks like a rocket. Close enough. It's on the surface of the Earth. So the Earth being a sphere, we're going to want to know its distance from the center of the Earth. So that's the radius of the Earth. And this thing is going to be moving at the beginning. So let me try to squeeze in some speed lines there. So yeah, it's moving, so there are speed lines. And what is our final sketch going to look like? Final sketch. All right, the Earth will still be there. So there's the Earth. And now this thing has gone all the way up to about, well, it says 2 Earth radii above the surface. So here's our rocket. And this distance here, this is 2 times the radius of the Earth. And of course, the distance from the center of the Earth to right there is 1 times the radius of the Earth, which means this whole distance here, and this is going to be important, is going to be 3 times the radius of the Earth. So hopefully by making the sketch, you can see why this is. Yeah, physics teachers, we love sketches. Sketches make everything nice and easy, and it makes the ideas much clearer. So let's pick a color. Let's go with green for actually doing this stuff. So what is our one with everything kind of idea that we're going to use to figure this out? It's going to be the law of conservation of energy. So sigma E initial plus sigma work external equals sigma E final. Okay, so this first term, sigma E initial, look at the initial sketch and ask yourself the questions. Is it moving? Yes, it's moving, which means we have KE initial. We definitely have that. Now our GPE question, is it infinitely far away from the mass we're dealing with? No, it's not infinitely far away. It's on the surface of the Earth, which means we're going to have to deal with gravitational potential energy. So we have GPE initial. And of course, there's no springs or anything like that. Is there any external work? No, there's not going to be any external work. We're ignoring air resistance and all that stuff. So that's just going to go away. Now let's look at this other term, sigma E final. So look at your final sketch. Is it moving? No. When it's at this point, this is when it will just run out of kinetic energy and it's about to fall, start falling back to the Earth. But at this point, it's not moving, so there is no kinetic energy. Is there GPE? Yes, there's still going to be GPE because we're not infinitely far away from the Earth. So we are going to have to worry about GPE final. So hopefully that's making sense. Now let's change colors to go on to step 3. So step 3 is going to be do the math. So turn the things into the things. Kinetic energy initial. Well, our formula for kinetic energy is 1/2 m v initial squared plus GPE initial. So look at your footer and find the formula for GPE. That's going to be minus big G. I'll use little m to be the mass of the rocket, and I'll use big M to be the mass of the Earth. And what's its initial distance in the initial sketch? That is just the radius of the Earth. So we've got that. On the other side, we have GPE final. So what's this going to be? this is going to be minus big G, little m, big M, divided by the final distance. So what's the final distance? Well, look at your sketch. That's this number right here. 3 times the radius of the Earth. So look at the pictures, look at the algebra, convince yourself that that's making sense. So let's pause for a second and reflect. What are we trying to solve for here? We're trying to solve for this guy. So one thing we can do right away is we can divide little m out of everything. Because there's a little m attached to every single term, we can just divide that away, which is good because, yeah, look at the question. I haven't told you the mass of this projectile, so fortunately for us, it's just going to disappear. So if I divide everything by little m just disappears everywhere. So that's good. And then let's do a little bit of algebra. That's going to give us 1/2 v initial squared is equal to, so I have negative big G, mass of the Earth, over 3RE. That's this term right here. And then I'm going to add this term to both sides. So that will end up being a positive big G, mass of the Earth, over radius of the Earth. So where do we go from here? There's a couple different things we can do. We could multiply by 2. Let's turn this thing on the right side that's the sum of two things. Let's do the little bit of algebra we need to do to get this to be just one big fraction. So if I multiply this last term by 3/3, that's going to give me a common denominator. So let me get a little bit more room here. So yeah, let me actually write that out so it makes more sense. 1/2 v initial squared is equal to minus gm. I got a little weird. I put the big G on top. So that's this term right here. And then this times 3/3 is going to give us plus 3 big G, big M, over 3RE. Okay, so common denominator. How do I add these fractions? Well, minus GM over 3RE plus 3GM over 3RE is going to give us 2 big G, big M over 3RE. And all of this is equal to 1/2 v initial squared. So the next thing to do is multiply everything by 2. So left side and right side by 2. That's going to give me v initial squared is equal to 4 big G, big M, over 3 times the radius of the Earth. So I'm almost there. I've just got to get rid of this squaredness. So we'll just take the square root of both sides. Square root. Try to draw a big square root so it's clear that we're taking the square root of the whole thing over here. And then ultimately, what will that give us? That'll give us, let me give myself some more room. On the left side, v initial is equal to big square root times 4 times g, so 6.67 times 10 to the minus 11th, and I'm going to be lazy and leave off the units, times the mass of the Earth. So what's the mass of the Earth? Let's scroll up a little bit. The mass of the Earth is this guy right here, 5.97 times 10 to the 24th. 5.97 times 10 to the 24th kilograms. And this is going to get divided by 3 times the radius of the Earth. So what is the radius of the Earth? The radius of the Earth is this number right here, 6.38 times 10 to the 6th meters. I already forgot it. 6.38 times 10 to the 6th. So we've got all this. So this is not the nicest thing in the world to do in the calculator. So again, if you're good with the calculator, you can do this all in one big shot. And if you're not so good with the calculator, you may want to take it in little pieces. So you may want to do the whole numerator, get that number. Let me write out what that would look like. You may want to do the whole numerator, get that number, do the whole denominator, get that number. And then remember, we still have to take the square root of the whole thing. So you would numerator by denominator, you would end up with the square root of some number, and then you would do the thing. So let me do this myself quickly in the calculator just to check my work. So 4 times 6.67 EE minus 11 times 5.97 EE 24. And now I'm going to hit enter, which is actually optional. You wouldn't have to. And then I'm going to hit divide by 3. And then I'm going to hit divide by 6.38 EE6. So if I do all that, let me show you kind of the intermediate step I have here. So I would have V initial is equal to 832.18181. Well, that's sloppy as crazy. That's fine. 82. Is this my answer? No, this cannot be my answer. This number here is actually, it's way too fast. That's not going to work. The reason is I haven't dealt with the square root yet. So how do I get the square root of this? You can write this number out and then use the square root function. The easiest thing is if that number is just sitting there in your calculator, raise it to the 1/2 power. So in my calculator, that is the button that is X to the box. This is how you raise a number to a power. So at this point, I'm going to hit X to the box, and I'm going to hit 0.5, because raising something to the 1/2 power is the same thing as taking the square root of that thing. So now I have 9,122 meters per second. So I put a box around it, and then I do step, does this make sense? Well, we solve for the right thing. We solve for V initial. It's in the right units, meters per second. And let's think about this number. It's pretty fast. 9,000 meters per second is about 18,000 miles per hour. But if you remember what the escape velocity from Earth is, escape velocity from Earth is something like this. It's about 11,000 meters per second. So this number is very big, but it's still a little bit less than that, which makes sense. Because remember the problem we're dealing with. We're launching this projectile. If we look up here at the sketches, we're launching this projectile pretty quickly, but not quite with escape velocity. So this thing's going to get pretty far away from Earth before it starts to fall back down, but it's not going to get infinitely far away. So it makes sense that we do, in fact, get a very big number. So we are happy with this. So we will give it a little check. So hopefully that makes sense.